I'm Bob Sanders. I'm the president of the Northern California Science Writers Association. So thanks for joining us this evening for an interesting talk by Daniel Swain about extreme weather in California and the Pacific Coast. He's a climate scientist. He has various appointments. One of his primary ones is at UCLA's Institute of the Environment and Sustainability, but also he has a joint appointment with NCAR, the National Center for Atmospheric Research. He's a fellow in the Capacity Center for Climate and Weather Extremes. And he also has an appointment with the California, he's a California Climate Fellow at the Nature Conservancy in California. He's a specialist, specializes in California weather. And in fact, he has a blog on Weather West, which is always interesting. And in fact, if you go there today, you can find out some sort of negative news about the current dryness in California and what that might mean. Maybe he can make a few remarks, or maybe he's planning to talk about that as well, what the previous winter has left us with for the rest of the year. So Daniel, thank you very much for joining us. I'll let you take over, and I know you have some slides. And what we're going to do is we're going to mute everybody during Daniel's talk, and then at the end we'll you can post questions you have or raise your hand in the chat, and we'll call on you and unmute you to ask a question of Daniel relating to his talk. So Daniel, take it away.
Great. Thank you for that introduction. And I'm just trying to share my screen now. Let's see. All right. Hopefully what's showing is the cover slide right now. I'll proceed unless somebody tells me otherwise.
Yep, go ahead.
Great. So what I want to talk about today is climate change and how this warming climate is affecting extreme events in California. And before I do that, I just want to briefly acknowledge, as was already mentioned, the folks and the institutions who have sort of made my scientist communicator role possible, not just the research that I do in an academic context, but also my availability to interact with and engage with journalists and other folks on a really sustained and regular basis. So it's expected that that's a significant part of my time commitment within these institutions, and that's actually pretty unusual. It's unusual that institutions like UCLA and NCAR and the Nature Conservancy are willing to support that level of engagement sustained over years. So I'm really grateful to them and to the Nature Conservancy, actually, in particular, given the level of funding they've been offering for that particular aspect of my role right now. So I just thought I'd start with a relatively quick primer on California climate. And I think that's useful because there's a lot that we take for granted here along the West Coast that's actually pretty unusual in a continental context and really even in a global context. But California really exists on the edge in a variety of ways, but from a climatological perspective, I mean that in the sense that California exists at a climatological boundary between the really stable and dry subtropics to our south and the much more active and moist mid-latitude climate regime just to the north. And that boundary is not static. It changes over time on a variety of timescales from year to year when we go from things like the El Nino to La Nina cycling. It changes from season to season. That boundary is much farther to the north in summer, which is why it's always dry in the summer, and much farther to the south in winter, which is why it's the wet season. And it also varies even within the wet season. For example, all of our midwinter dry spells are when that boundary effectively moves north, and all the wet spells are effectively when it moves south. So our day-to-day weather and our climate is really dictated by our position on this boundary that varies quite a bit in time. And one of the consequences of being there on that boundary is that we have a strong seasonal cycle of precipitation. So as I mentioned, that boundary is farther north in summer and really far south, or relatively far south in the winter. And so that is largely why we have such distinct precipitation seasonality in California. And while folks often joke that California doesn't really have seasons compared to other places, in some ways the seasonality of rain and snow is actually even more pronounced than in places that are famous for their changeable weather conditions and their really distinct seasons. Because in summer you can really reliably predict that it isn't going to rain in San Francisco in July or August. That's not true in most places. In fact, the coincidence between the dry season and the warm season is unusual in a North American context. In most parts of the country, it's actually relatively wet in summer compared to winter. So that becomes important later when we're talking about wildfires. And all of this also gives California sort of uniquely high year-to-year variability in precipitation. That's something you can see on the map at right, really just showing the level of variation in California is a lot higher than anywhere else in the United States by a pretty wide margin. And so one of the consequences, or one of the reasons for that, is that we have this really defined winter wet season. There really only are a few months out of the calendar year when California sees most of its water arrive. And so if we miss out on the precipitation over the course of just those few months, we're pretty much out of luck for the rest of the year. So that lends itself to large year-to-year variability and also to particular drought susceptibility, because if we miss out on that precipitation in winter, there's no way we're making up that deficit the rest of the year. So, as is probably not a surprise to anyone on this call, California's climate is already different than it used to be 40 or 50 years ago. But increasingly, it's different even than the climate that was in place just a couple of decades ago. So the rate of change has accelerated in recent years. We now live, in California in a much warmer place, along with the rest of the world, in a place that receives already less snowfall in the mountains than it used to. The mean snow line is increasing as the mean snowpack decreases. And we've seen, once again, not a surprise, but a large increase in wildfire intensity and severity recently. And these are all things I'll talk a little bit more about in a moment. But I want to jump right in to some of the kind of findings that we've made over the past few years, which really point to a future that is, I think, somewhat different than a lot of folks might have assumed, especially because right now, once again, California is dealing with a pretty severe and deepening drought, as was the case not so long ago. Earlier in the past decade, California saw its worst drought on record. So this is now the second major drought this decade in California. We've seen lots of wildfire. So we're thinking, why are we talking about flood risk and extreme precipitation in the middle of a drought when we're dealing much more with water scarcity than the opposite? But the reality is, interestingly enough, there is not much indication that the overall average amount of precipitation in California is likely to change, even in a much warmer world. And in fact, there's actually not a lot of evidence that it has changed to date, despite all the drought we've been seeing. If that seems a little bit counterintuitive, that's understandable, because really what we find, both in observations and in projections for the future, is that California is likely to experience a large increase in both very wet and very dry conditions, despite little change in the mean. So if you think it feels like we're seeing drier conditions, you're right. If you feel like we've been seeing wetter conditions, at least occasionally, you're also right. And it turns out the way the math works is that averages out to something that kind of looks like the past, except for any practical purpose, this really doesn't resemble the past at all. So this is a case where looking at the arithmetic mean is really missing the point, potentially, and masking what we find to be a pretty strong trend in projected precipitation whiplash, is the term that we coined to describe this. And so why do we care about this? Maybe it's obvious, but certainly to some folks I speak with, it's not. just by means of an example, I think we can look back. There's now several examples since I created this slide a year and a half ago, unfortunately, but this is probably the most dramatic one still. If we think back to December 2017, when the Thomas Fire occurred in December in Ventura County and became the largest wildfire in modern California history at the time. It has since been eclipsed twice in the past 3 years or 2.5 years. But when this occurred, it caused a lot of damage. It burned a large area at very high intensity in Ventura and Santa Barbara counties, and then was immediately followed by a powerful atmospheric river storm that dropped over an inch of rain in just 15 minutes in the burned canyons and created really devastating debris flows and mudslides. They actually killed a lot of people and destroyed a lot of homes. This was a really high profile event. But mathematically, if you just take the average of the meteorological conditions over that month and a half period, it was, for most of the time, mostly sunny and breezy with below average precipitation, which doesn't remotely describe any of these really devastating events that occurred in the same window of time. So really, if we're only considering changes in the average climate, we're often going to miss the point, especially when it comes to extreme events. Another example, I mentioned there were a lot of these. You may recall the near catastrophe at Oroville Dam back in 2017, early in the year. This followed what was just a year or so previous, the most severe drought on record in California. And these images are just less than 2 years apart from one another, depicting the same body of water during the drought, and then in the aftermath of what almost was a really big disaster as a result of the failure of the spillway at Oroville Dam. So while weather and climate didn't cause the Oroville Dam crisis, ultimately it was an engineering failure and a question of perhaps insufficient imagination from a civil engineering perspective. But really what happened here fundamentally was that we did have an extreme atmospheric river storm event that turned that engineering issue, that failure of the primary spillway on the dam, into a genuine crisis, because when they couldn't use the primary spillway anymore, they started to use the somewhat euphemistically termed emergency spillway, which was essentially a dirt hill on the side of the dam, which unsurprisingly eroded heavily and then headward back towards the dam. So there was a serious concern at one point that erosion could result in a large collapse and a wall of water rushing down the canyon. What's interesting, though, is that the historical warming that's occurred over the 20th century, just the warming alone, even if you don't take into account any change in the amount of precipitation, but just the fact that the temperatures were a few degrees warmer than they would have been 40 or 50 years ago, that probably increased the inflow into Oroville Dam during that event by about 30%. And that's a margin that would have made the difference between the emergency spillway being overtopped or not. So that turned so you could argue that the warming that's already occurred turned what this engineering issue into a crisis. Now, if you think 20 or 30 years into the future, you imagine this event happened in 2030 or 2040, if you add another 30% onto that inflow into the dam, the hypothetical outcome there is once again very different and potentially a whole lot worse than what actually happened. It's very conceivable that we would have seen an actual failure on the dam had this event occurred a couple decades from now rather than in 2017. So something else I think that's gone a little bit underappreciated in California is the importance of the precipitation seasonality in this part of the world. And I've already talked about why it's unusual in a broader geographic context to have a dry summer and wet winter cycle. But what we find is that in addition to this increasing precipitation whiplash from year to year and from season to season, we also see something that we've called seasonal sharpening. So which is essentially this notion that we're likely to see drying trends in what are effectively the shoulder seasons for precipitation, the autumn and the spring, and potentially an increase in the precipitation that occurs at peak season in the middle of winter. So what this really means is that the wettest times of year may actually get wetter, but that every other time of year gets significantly drier. And that's going to cause a lot of problems. And I'll talk a little bit more about that in a moment, but just by means of summary, this narrowing of the rainy season has big implications for wildfire risk, for our snowpack, and subsequent water management issues, as well as for ecosystems and agriculture, because it extends the season during which irrigation water is needed. So we'll get back to that a little bit more in a moment. But all of this leads to what is arguably a bit of a paradox, which is this simultaneous increase in both water scarcity, but also water overabundance at the same time and for the same reason. So if we see less autumn and spring precipitation, but more winter precipitation, and we see more precipitation on fewer days with more intense storms, but fewer of them, and less snowpack, but more evaporation, all of that put together really paints a picture of a pretty stark increase in the kinds of events that are most problematic from a weather and climate perspective in California, which is to say an increase in the risk of both drought most of the time, but also flood the rest of the time. And on the flood point, because I think it's something that gets maybe less attention than it should, probably because we've been dealing with so much drought and wildfire and water scarcity recently. But California, if you take the historical view, actually has quite a precedent for really devastating and massive flood events. What's effectively known as, or what has been termed by some, California's quote, other big one, with the original big one being a large magnitude earthquake in San Francisco or Los Angeles, which would obviously be devastating. The other big one is a repeat of what's also known as the Great Flood of 1862, which is effectively a month-long deluge from a series of atmospheric river storms. And it was once thought that the event that occurred in 1862 was an exceptionally rare event, something that might happen every 1,000 to 10,000 years. Turns out that that was a very inaccurate estimate, and that really what happened in 1862 is something more akin to an event that would happen every 1 to 200 years. So in other words, it's a lot less rare than we thought it was, and it's a lot more likely that it may recur in the modern era than we previously thought it was as well. And when it happened in 1862, it filled up a good portion of the Central Valley, well over 100 miles long, and in some cases 40 miles wide, essentially turning it into a temporary inland sea. The state capital was temporarily relocated to San Francisco because the existing Capitol grounds in Sacramento were underwater for weeks at a time. And it's pretty obvious that a modern day repeat would be disastrous for California. And this is actually something that we're working on right now as a project, trying to figure out exactly what this would mean, because there's a respectable chance that it could occur. And on that point, our recent work suggests that there is something like a 50-50 chance of a modern recurrence of an 1862 level flood event in California over a 40-year period beginning last year. So really what this tells us is that the likelihood of an event like this was higher than we used to think it was in the first place. The odds are also rising as a result of increasing atmospheric water vapor due to climate change. So we dove into this a little bit more deeply in some work from last year, looking specifically at California's most extreme atmospheric river storms. So not precipitation on average or overall, not run-of-the-mill storms, but we wanted to take a look at the narrow subset of storms that cause the biggest problems, the biggest of the big. And just to summarize what ended up being a pretty lengthy investigation, what we find is that as the climate warms, the most intense atmospheric river events are likely to become quite a bit stronger, mainly due to what is arguably one of the most straightforward effects of climate change, that warming temperatures increase rates of evaporation, increase the water vapor holding capacity of the atmosphere at an exponential rate, and result in what are likely to become historically unprecedented atmospheric river storms and subsequent flood events as we go through the 21st century. And so I honestly think that flood risk is one of California's larger, if unappreciated, risks in a warming climate. Clearly, droughts are a big problem and becoming a larger problem. wildfires too. And I'm going to talk more about that in the second half of the talk. But flood risk is increasing, not just in California, but more broadly. But California is actually a hotspot region for that kind of risk in a warming climate. And it is entirely possible that we will see events that result in widespread and deep inundation in places that take people but really by surprise. And so there's this serious question about exactly how our flood protection infrastructure, which is not necessarily up to par in all cases. I know the Army Corps is concerned about some of the dams in California and some of the older levees in areas outside of urban areas. These are significant points of concern in a climate where the plausible worst case flood is probably a lot larger than we used to think it was, and certainly larger than we were planning for when these structures were constructed for the most part in the early to middle part of the 20th century, before climate change was a significant issue. And before I jump into the wildfire part of the talk, I just wanted to interject this brief aside on what's now known as extreme event attribution. So really what this is a framework to answer questions about specific individual extreme events and their potential link to climate change. So I think asking whether or not climate change caused a particular event is almost always an ill-posed question that really can't be answered as such. But in science, one of the things we try and do is reframe questions so that they become tractable. And what we've essentially done with extreme event attribution is just that. And the reframing goes something along the lines of, to what extent is human-caused climate change responsible for some aspect, whether it's the occurrence or the intensity or something else, of a specific extreme weather event? And the good news, I suppose, at least from a scientific perspective, is that that framework now exists. We can address, this is now a tractable question that can be asked and in many cases answered with somewhat high confidence, or in some cases with quite high confidence. Depends somewhat on the physical event type, whether we're talking, for example, about a heat wave or a flood or a hurricane or a wildfire. The level of confidence we have in extreme event attribution statements varies pretty strongly based on what type of event we're talking about. But in general, this has gone from being something where you might hear, oh, we can never attribute specific events to climate change, to now saying, well, actually, in some cases, we effectively can. And so that's been a big shift in the last few years. I think there have been some pretty big advances in the field. And there are some pretty big implications, not just for the physical science, but also for, I think, public policy, legal liability, and also just the public perception of the link between daily weather and climate change. And so if you're interested in this framework, our primer on this is freely available. So this was published just last year, and is the original source for this nicely adapted figure that was provided by one of the Science Writers Association members for one of her pieces recently. Okay, so the second half of the talk, I really wanted to focus on wildfire because it's unfortunately ever present in California, and I think we're likely headed for another bad fire season in California and throughout the West. And I just want to first remind everybody that wildfire is a natural process. It's a complex biogeochemical or system process. And wildfires are, well, simply fires that are primarily fueled by vegetation. And that vegetation can take many forms. It might be trees, it might be grass, brush, just about anything in between. But the fundamental thing here is that fire is a natural part of the landscape that has been around really since as long as there's been organic matter that can potentially combust on the surface of the earth. So it goes back quite a long time. But susceptibility to wildfire is a function of both the background climate conditions and also the local vegetation conditions. And both of those are dynamic, they vary over time. And what that means is that a wildfire can technically occur anywhere there's a substantial amount of vegetation. And this is often missed in certain circles that you can actually get fires in unexpected places. One of the largest forest fires in US history, for example, occurred in Wisconsin and Minnesota. Some of the greatest wild and urban interface fire risk zones outside of the West in the US are actually in New Jersey, near the Pine Barrens there. And there are wildfires even in very moist subtropical places like Florida or Hawaii. So fires occur across a really wide range of regimes, and that's not unusual. But the level of fire that occurs in a semi-arid place like the American West is greatly elevated. So even though you can get big fires in, say, central New Jersey, you don't get them often. And the reason for that is that the conditions, the preconditions, both having dry vegetation and conducive weather conditions to spread a big fire, happen very occasionally there. Whereas in California and a lot of the rest of the West, it's almost the default state for multiple months out of the year. It gets elevated from that background state occasionally, but in general, conditions are liable to burn for multiple months out of the year. And also, wildfires are not all created equal. You can get high intensity fires and low intensity fires, and uniform burn patterns versus mosaic burn patterns. And all of this is really important when you think about the adaptedness or not of various ecosystems to wildfire. Many ecosystems are very well adapted to at least periodic low to medium intensity fires. Some of them are even fire dependent in the sense that certain species can't reproduce without fire. So this is a critical part of the landscape. But the problem is, well, the fact that now we're in the way, we're changing the climate, we're changing these background preconditions. And so we've seen, as is probably a surprise to no one, a really dramatic increase in California wildfire over the past, well, in recent decades, the trend was apparent. And then in the last 5 years, things really exploded. Just since 2015, 9 of the 20 largest fires in modern California history have occurred. 6 of those occurred just last year in 2020. But more importantly, 15 of the 20 most destructive fires in California history have occurred in the past 5 years, 5 of those just last year, and 7 of the 20 deadliest fires, 2 of which occurred just last year. So there's clearly something different about the most recent decade. And I think just to put this into perspective, now more people in California have died in wildfires in the last 3 years than have died in any earthquake in California since the Great Quake of 1906. So I think the scale of what's going on, certainly from a natural disaster management perspective and from a public perception perspective, wildfires have really eclipsed earthquakes in the public eye because we haven't had a really big earthquake in a long time, and we have had just innumerable really terrible fires in a way that we really hadn't seen previously in living memory, or even really in the 20th century in this part of the world. So what's driving this escalating wildfire crisis? Well, there's really 3 key pillars. And the first of which is, well, the expansion of populated areas into high-risk zones. There are simply more people living in harm's way than there used to be. There are more structures built in places that are highly flammable. And that is a significant reason why we've been seeing so much more destructive and deadly fires. The next pillar is the legacy of 20th century forest management. And by that, I mean something pretty specific, which is the exclusion of natural fire from a lot of these forest landscapes for the better part of a century. We essentially removed all of those beneficial natural low to medium intensity fires during the 20th century and the early 21st century, greatly to the detriment of these ecosystems in a lot of cases. And we now have forests that are massively denser than they would be in their optimal natural state. And so there's a great deal more potential fuel for these fires in a lot of these overgrown forests than there used to be. And it's really hard to sort of make progress on this problem now because, of course, the cat's out of the bag. The forests are what they are right now. And we also have the third pillar to contend with, which is climate change. And these first 2 pillars are important, but not necessarily universal. Obviously, the expansion of urban areas into high-risk zones is only relevant in places where you have significant populations of people. It's not relevant out in the remote forests out west. The legacy of forest management is important in the forests, but then also a lot of the fires in California are not really forest fires. They're burning in other sorts of ecosystems other than forests. So that can't be true and relevant everywhere either. But climate change is pervasive. It's acting everywhere across the landscape. It's relevant in all types of ecosystems everywhere throughout the West. And so it's really acting as a threat multiplier that's amplifying the effects of these first two pillars. The unfortunate thing is that they're all pointing in the same direction. I think that's why we've seen such an acceleration recently. It's not just one thing, it's a bunch of things coming together all at once. So what is the role of climate and how does that work? So really, it's actually almost as simple as it sounds. In fact, it's maybe even more simple than it sounds. As temperatures rise, the gap between how much water could be in the atmosphere and how much is actually in the atmosphere, which is known as the vapor pressure deficit, is increasing. So in other words, as the air gets drier and evaporation increases, unless you're greatly increasing the amount of water on the landscape, which would have to come from increasing precipitation, which I've already shown you isn't happening, then that moisture is coming at the expense of soil moisture and water in rivers, lakes, and streams. And because of that, what ends up happening is this increasing water demand plus the increasing soil water depletion as things get warmer and we don't see commensurate increases in precipitation, it dries out the vegetation. First, it starts to dry out the dead vegetation. So that would be the seasonal grasses at the end of summer and whatever branches are lying on the ground, dead trees. But at the end of the season, as we get towards autumn, the end of our long dry summers in this part of the world, it also starts to dry out the living vegetation. So even the plant tissues that are still connected to the soil, that can still draw water out from the soil column, start to get increasingly dry towards the end of the season because essentially there is no longer as much water left. In some cases, there's very little, if any, water left by the end of the season. And so these plants become really dry, both the living and the dead vegetation on the landscape. And so as a result of this, about half of the observed increase in Western US forest fire area burn can be directly attributed just to the warming that had occurred as of a few years ago. So anything that happens from a few years ago forward is really in addition to that increment that we've already seen. And so our own work from last year really focused on the importance of autumn extreme fire weather conditions. And in California, what we found is that, and this was surprising, this was a big number, even to those of us who've been looking at this for a long time, climate change has already doubled the occurrence of extreme fire weather conditions in autumn specifically, just since the early 1980s. That's a big increase because it was not a small number to begin with. And what's really happening is that climate change is affecting the character of wildfire. So it's increasing the severity and the intensity of these fires rather than the number of fires. In fact, interestingly, there really hasn't been an increase in the number of fires in California or throughout the West. In some places, there's actually been a sustained decrease. But those fires are becoming much larger, much more destructive, and much more intense. And that really has to do with these changing background conditions, the vegetation preconditions that are becoming drier, and these fires are able to burn more intensely and more explosively. Again, because they're nonlinear processes of combustion, the hotter they burn, the more exotic fire behavior they can produce, including these giant fire thunderstorm clouds that effectively produce their own local weather systems, and in some cases can even result in lightning, strong winds, and in a couple of recent extreme examples, essentially fire tornadoes. That was something we hadn't seen much until recently, but we've actually seen it multiple times over the past few years. And again, why is this all happening? It doesn't need to be a particularly complicated process. Mostly it's as simple as when it gets warmer, without an increase in precipitation to offset it, the vegetation gets drier and the fires burn hotter and more intensely. But there is also something else going on in California specifically, and this is a California specific aside that is not so relevant elsewhere in the West. The seasonality of our precipitation is really important, as I mentioned earlier, and it is changing. And it is really important to know that fire seasons are not just getting longer, but in particular, they're getting longer on the back end in autumn when vegetation reaches its driest level of the year. And this is different than if fire season were lengthening mainly because of increases in the spring. That would be much less of a problem because in California, the vegetation in spring is really maximally moist, but then it dries out progressively throughout the summer and into the early autumn months, really until the autumn or winter rains arrive the following year. And so as the autumn rains become progressively more delayed, and they have become about a month delayed already from what they were historically, as that happens, not only do we prolong fire season, not only do we make the vegetation drier at its peak in the autumn than we used to, but we also increase the temporal overlap between maximally dry vegetation season and offshore wind season. So these are those Santa Ana or Diablo or Jarbo Gap winds that we see in Northern California that blow from land to sea. These are those red flag days where you just feel like you get chapped lips and you can't put enough hand lotion on. Those are these desiccating offshore winds, and they don't occur during the summer, interestingly. So they don't occur at the hottest time of year. They actually occur during the transition season as we go from autumn into winter. But if we delay precipitation, increasingly these strong offshore winds overlap with the maximally dry vegetation more and more. And so we've not only increased fire season, increased the magnitude of dryness of the vegetation, we then also have sort of this nonlinear effect where there's a much longer portion of peak offshore wind season that's occurring when the vegetation is really dry. So it's sort of a triple whammy effect there. And so I think this is why we're sort of coming to terms with this new abnormal for California wildfire. I think that was Jerry Brown's term a couple of years back, because a new normal, as some folks use, really suggests that we've reached some semblance of a new stable plateau, whereas really we're still on the upslope of the roller coaster, and there is going to be further warming in California. How much warming is still largely up to us and going to depend on global progress on bringing carbon emissions to net zero as quickly as possible. But since that isn't happening tomorrow or this decade, there is going to be more warming before we really stabilize the climate. So the question is how much? But the answer to will the wildfire problem get worse is yes, because we know there is going to be at least some additional increment of warming, and it could be quite a substantial increment. The climate component of that risk is going to get worse before it gets better. And of course, there are follow-on implications for fire-related or fire-adjacent hazards like post-fire debris flows, like we saw in Montecito, or water or air quality issues, as we've seen in the past couple of years. And I just wanted to provide some imagery, just as an illustration that this is not just a California problem. California sees autumn wildfires most years. That's not necessarily new. But this past year, much of the interior West saw extreme wildfire behavior as well. And I just wanted to play this brief clip of a large fire vortex. I actually took this video just north of Boulder, Colorado in mid-October this past year. And it just goes to show you that in a place that would normally have snow on the ground that time of year, it snows along the Front Range pretty early in the season. This is the kind of fire behavior that the current climate conditions are sustaining later and later into the calendar year. So just suffice it to say, we've got a pretty big problem. But what is the essence of this problem really? I think this really gets to the heart of the matter, because the problem isn't the fact that there are wildfires in the West. The problem is that what we're seeing are these catastrophic fires in the wild and urban interface, really in that interface between where there's flammable vegetation and where people live in homes. And that's an accelerating crisis for sure, but it's not inevitable. We've seen really countless tragic examples recently in California and in other places of these huge fires that have just taken out city block after city block in really horrifying fashion that we hadn't seen really on the scale in the 20th century. This was thought to be sort of a problem that we solved with modern firefighting in the mid 20th century. And it's coming back to haunt us. But I really just want to emphasize that wildfire itself is not inherently bad. It's the intersection between wildfire and populated areas that's becoming really catastrophic. And we haven't necessarily seen the worst that's possible. We could still see worse in the future. So the real question in my mind, in the mind of a lot of the climate scientists and fire ecologists that I work with, is how can we decouple fire from catastrophe? Because the two things are, one is inevitable, but the other is not. And I think this ties in with the overall picture and the theme of this talk with flood and drought and fire. What we really need in California and elsewhere, but especially in California, to cope with increasing extremes is going to be increased flexibility in our adaptations to climate change. Because the physical reality is that we're going to see an increase both in precipitation intensity and overall water scarcity. At the same time, we see a loss of snowpack and longer and more intense fire seasons. And so one of the questions is, can we mitigate flood and drought risk simultaneously, sort of by pitting one against the other? And can we do something similar with fire by using good fire to prevent bad fires, all while maintaining some level of environmental co-benefits in the process? And I think the answer is yes, we can do this, but we're not doing it yet. And we need to start doing it soon if we're going to stay ahead of some of the things that might be coming down the pike. And so it's becoming really clear that historical paradigms and water and fire management practices really aren't going to cut it in the 21st century, but we do have some idea of what might work. And so I'll leave some closing thoughts, and I think we'll have plenty of time for questions. But climate change has arrived, and California is really already a different place than it was when 20th century policies and infrastructure were initially put in place. And a plausible trajectory for our future climate in this particular part of the world is, well, warmer year-round, probably unsurprisingly, with less snowpack and more intense but less frequent storm events, as well as a narrowing wet season and a lengthening fire season. And we will probably see large further increases in wildfire and flood risk. But the real question at this point is, how do we make the increase in these physical events less problematic? How do we decouple these increases from the physical hazard from their potentially catastrophic outcomes on society? And so the physical science suggests that we do need to be flexible in all of this in the face of increasing extremes, but also that we're not always going to be able to build our way out of these challenges, and that we may have to take a step back in assessing what the most plausible path forward may be in a warming climate. So with that, I just have some of my contact information up here, and I think it's time for questions.
Thank you, Daniel. Yeah, I've asked people to raise their hand or post us, some possible questions in the chat. But while we're waiting for some of those to come through, I just had a question. You mentioned that the fact that we've built into the wildland interface much more, and that's one of the issues. But I think also in some of the fires that happened here in around the Bay Area, was it in the early fall or late summer? So many of those fires were actually not necessarily threatening a lot of communities, but it sure created a horrible atmosphere in the Bay Area with macabre orange skies. So, I mean, even without the building into the wildlife interface, it seems like more fires in the future are just going to be more pollution and some horrible weather during the fire season.
Yeah, it's actually a really interesting question that we've been getting a lot, because one of the most effective interventions is likely to be an increase in the use of prescribed fire, so intentionally burning more in a more controlled way. And a lot of folks say, well, aren't you still going to have the smoke problem either way? And obviously, you're going to generate some smoke, so that there is going to be smoke either way. But what's really interesting is you would never get that kind of apocalyptic Blade Runner sky from a prescribed fire treatment, because you generally burn at a much lower intensity. So, and this is interesting from a carbon emissions perspective. Often when you do prescribed fire treatments, you burn the same land at a lower intensity that might burn accidentally or in an uncontrolled way at a much higher intensity. You produce vastly less smoke, vastly less carbon emissions. It's like orders of magnitude less. And so there probably is going to be some significant level of smoke at times in the future, no matter what. But the lower intensity fires just don't produce as much air pollution, nearly as much air pollution as these massively intense ones we've been seeing recently.
Right. Thanks. We had a question from Andy Fractal. I don't know if you want to ask that, or should I ask it for you? Do you want to unmute yourself? Or maybe I can ask it for you. Andy says that if you had $100 million from the California budget, what would be the first thing you would do with it? 100 million is not a lot, but
well, I'm assuming in a climate capacity. There's a lot of other things that $100 million could go toward, I think, at the moment. But I think that I think a lot of it probably could go towards really ramping up the use of prescribed fire, actually, because it's expensive. $100 million would be a helpful amount. It would actually make it would definitely move the needle on this. But it's right now, that's actually been one of the problems, is that the funding for doing these kinds of prescribed fire treatments, the Forest Service, CAL FIRE, they have budgets that often end up getting eaten up by disaster response. We're constantly in response mode, and it's really difficult to be proactive about these things if you have a fixed budget and you're also tasked with responding to catastrophe. I mean, disasters are really expensive. So I think that could actually be a really good use of the money right now, and would probably have and the other thing is it would have tangible benefits almost immediately. So this is not something you have to wait a few decades for the benefits to be known. The benefits accrue the moment the prescribed fire is completed, essentially.
we got another question. Are all Mediterranean climates experiencing this sort of wildfire, lengthy wildfire seasons?
Well, it is a lot of Mediterranean climate regions do tend to have severe wildfire risks. So it's common, in the southern Mediterranean itself, in that part of the world. It's also true in other regions that have Mediterranean-like climates, like the west coast of Chile, the southwestern Cape of South Africa, parts of southern and southwestern Australia. These are all places that have similar types of Mediterranean climates and also have not just high fire risk, but have urban areas that periodically get devastated by large fires. What's interesting is in a warming climate, all of the other Mediterranean regions on Earth are actually changing in a slightly different way from California. Almost all the rest of them are getting significantly drier on average. So I said how California is not really drying on average, we're just seeing more extremes. The rest of these places actually are getting drier on average in addition to everything else. So this shared experience here and there with respect to wildfire is likely to be a shared experience where it's something that a lot of these places are facing right now, as well as places that do not have Mediterranean climates. Southeastern Australia, that had such a horrible wildfire season as well earlier in calendar year 2020, even though it feels like 15 years ago. That's a very different climate regime. They also had a terrible fire year. So did the Siberian Arctic. So very different places, climatologically, ecologically, and otherwise, are all seeing a pretty significant increase in the severity of fire as the climate warms for slightly different reasons, but the net effect is similar.
Kenneth Britton had a question, raised his hand. Can you unmute yourself and ask a question?
Sure. Great talk. Thank you. The question was about prescribed fire, that the very thing that you emphasized, which I think is really interesting about the narrowing of the fire season, also makes those shoulder seasons, which is when you can make prescribed fires happen, particularly in the late spring, kind of difficult. And I think they've had trouble with that up in Northern California, where the Native American tribes are working with that, but CAL FIRE only lets them work within a pretty skinny window. And if you want to expand that across California, it's hard. How do you solve that?
Yeah, that's a really good question. That is exactly the problem that's motivated our next big research push, which is how are prescribed fire windows changing from a weather perspective in a changing climate. And the initial answer is somewhat what you'd expect, is we're losing the autumn window. It's often just too dangerous to do this because of these shifts seasonality wise. But what's interesting is we may actually start to gain, amazingly enough, winter windows. You may be able to do this, not every year. Some years it's just going to be too wet. But in the drier years, you may actually have pretty significant opportunities to do winter burning. And even though spring is longer and maybe drier, there is still some spring window at some point. It may be earlier in the calendar year than it used to be, but there is still some period, right after the rainy season when the vegetation is going to be relatively wet. And so we're still going to have some kind of spring window. It just may be a different window. And the autumn window kind of seems to be less and less plausible, but then we might gain something in the winter. So there are probably going to be some ways to do this, but in order to do it, we're going to have to quantify that and then also get regulatory agencies to change their thinking. Right now, they do have specific windows, and they're not sufficiently flexible. So what we really need to be able to do is say we actually need to have dynamic windows. Like, yes, there will be some times where you probably should tell people you can't do this. It's too dangerous. It's not safe. But we're also going to have to be more flexible and say, windows of opportunity may arise at weird times. If you're ready to go, you can do it now. Hopefully that's what we move toward.
Kenneth had mentioned the indigenous people up in the north. Someone has asked, can we learn anything from the way the California Indians managed the land?
Yeah, there's actually some really interesting scholarship on how much of the fire problem in the Americas has essentially arisen because colonizers suppressed these traditional practices. There was so much cultural burning, not just in California, but really everywhere, for hundreds or even thousands of years before Western colonization, essentially. So there was a lot of fire in the landscape pre-humans, because occasionally there'd be lightning and fires would just burn and burn. There was nothing to stop them. There was also no humans in harm's way. And then once humans arrived, in addition to those natural fire starts, there was a lot of cultivated fire. So most of the native peoples of California actually used some form of cultural burning, intentional fire, which was almost always achieved at a pretty low intensity. It's effectively the kinds of prescribed fire treatments that everyone's talking about bringing back. So in a lot of ways, it's actually bringing back that traditional practice. There were other cultural reasons why those fires were conducted that are different from what Cal Fire, the state of California, is necessarily going to be trying to achieve. But I think that there's actually been some progress towards making specific tribes partners in this process, and I think there's been some frustration that a lot of the regulatory agencies are still saying, you need to do it our way, and the way that it's being prescribed is not necessarily even the most effective way. And I think that's tremendously frustrating. So I think that I'm hopeful this improves. In a lot of ways, it's bringing back something that was a traditional practice for a very long time before it was suppressed over the past 150 or 200 years.
Lisa Krieger is asking whether there may be land use restrictions that might have help us deal with these wildland urban interface fires.
Maybe, but I think it's hard to say to people you can't live here. Part of the reason why that's going to be difficult is that the cat's out of the bag. I mean, people already, in a lot of places, people already live in places that are greatly at risk. These populated areas already extend well into the wildlands. And so unless you're saying we need to remove people from where their current homes, I think that, we can be smart about not continuing to build, I think, in the highest risk zones. There's interesting work on recognizing what the truly highest risk corridors are. There actually are really specific, almost watershed-like corridors of risk that coincide with wind corridors. It has to do with the topography. Building in those places is probably not a good idea. I certainly wouldn't live there, but I think it's going to be, I think the pathway toward land use restrictions in that way, in that capacity, is a little bit harder to foresee than some of these other potential interventions, which is, you can build communities that are a lot more fire resilient too. We don't do that in California. You can build individual structures that are a lot more fire resilient. We build very flammable homes in community configurations that are especially flammable in places that are extremely flammable. That has been the historical practice. And so even if people continue to live and build in these places, if you do it differently, that can actually make a big difference as well.
Michael Barber, you raised your hand. You want to unmute yourself and ask the question? We can't hear you, even though you seem to be unmuted. Maybe we'll have to come back to you since we can't hear you there. Dan Macon, you had a question. Maybe you could unmute yourself and ask that. Dan, you there? You're talking about, maybe I can ask it for me. It says flexibility seems to be critical for livelihoods that depend directly on climate, like ranching. Do you foresee improvements in the accuracy of our predictive capacity on a timescale that will help land managers and ag producers adjust to these changes?
That's another good one. I think, one of the truisms in atmospheric science and climate science is that some of the most difficult time scale of predictability is the one that would probably be most useful to the most people. So we have really good weather forecasts. We're pretty confident in our long-term multi-decadal climate predictions. Everything in between is extremely difficult. So even looking out to like next winter, for example, is kind of a crapshoot still. And there are windows of opportunity where we can say, actually, this particular year, we have a really strong indication that next winter is going to be really wet or really dry. But on average, the year-to-year predictability, and talking about anything on the scale from more than a few months out going to, a few years out, is really difficult. And it is possible we make progress on this from a numerical modeling perspective. The main issue is actually we don't know the way the world is today well enough. We don't know spatially contiguous information about the condition of the Earth today. If we knew that really, really well, we'd be able to predict the short term or the medium term a lot better. We can get away with it with weather forecasts because we don't need to know all this precisely to look just a week or two out. But if we're talking about months to a few years, we would need to know the state of the oceans, the state of the atmosphere, the state of the sea ice, the state of the land surface, all of these things with great accuracy. And we aren't quite there yet. We're getting closer, but it's a long way of saying, I think seasonal prediction is going to remain tricky. Decadal prediction is going to remain hard, but there will be some advances. So right now we have really good weather forecasts and really good sort of quantifications of the envelope of weather conditions during a particular decade or something, but we don't necessarily have a prediction, say, for 2023 or 2024 with any confidence. And I think that's likely to remain for quite some time.
We had a couple of questions about groundwater. I guess the impact of these droughts or extreme weather events on the groundwater, and also whether there's anything we can do with groundwater that might ameliorate the changeability of the weather.
Yeah, I actually think that fits right in with the idea of being flexible from a drought and flood perspective. So we talked about using fire to mitigate fire. What I meant when I said using flood to mitigate drought is actually precisely this. And so this is the subject of another project that we're working on right now, another collaboration with the Nature Conservancy, thinking about how we can essentially harness floodwaters to recharge groundwater, because it may be the case that much of the time there isn't enough water to go around and there isn't an ability to store water in the ways that we've used to traditionally behind our large reservoirs on Sierra Nevada watersheds on the western slope. But what may happen if we get these periodic huge rain events and big flood events that the river systems and the channels essentially can't accommodate, what we're going to be doing is trying to figure out what to do with all this water without flooding Sacramento. And so, well, one thing you can do is you can deliberately inundate places that aren't Sacramento, that you've pre-designated as places that can help recharge groundwater. So essentially, you could connect these flood events to groundwater and use the floods literally to recharge the aquifers in the wet periods. And that's the rosy picture. It's a lot easier said than done in practice, of course, but one example, it's not really used for groundwater recharge. It's not really quite the right part of the Central Valley, but the Yolo bypass is a good example of something that you could see that could achieve these kinds of benefits if you located it somewhere where recharge was plausible. So the Yolo bypass is essentially, it's farmland that is periodically inundated on purpose when the Sacramento River is running high. So it takes pressure off the levees elsewhere in a way that's pre-designated. The farmers all have easements on this land. You could envision a future where large portions of the Central Valley had different levels of easement. If we get the 20-year flood, I agree that my almond orchard will be underwater for 2 months. If we get the 100-year flood, we can agree that it'll be underwater for even longer. And there can be structure in place so that most of the time it's land used as it always was, but occasionally and when needed, you can be flexible about that kind of agricultural land being used to recharge groundwater, and then also to reduce the flood risk in urban areas. And so that would require pretty big retooling of the way water is managed in California, and would require some level of additional infrastructure. But it's a lot less infrastructure than building new dams. It's a lot less infrastructure than rebuilding Sacramento after it floods. So the cost benefit analyses, I think, will work out very much in favor of those sorts of interventions. But the politics, of course, is a whole nother question of actually making that happen.
Speaking of that, Michael Barber's question is actually, how do you convince the public that prescribed burns are necessary, especially if they're near your home? And I think there's a lot of complaints about that.
Yeah. Yeah, and I mean, they're never going to be zero risk, and they are going to generate some smoke. So those are the downsides. But again, like with many other things, we really need to look at what the alternative is. And the alternative is having these ever more catastrophic, ever more uncontrollable fires that have a high likelihood of burning your house down, or a high likelihood of ruining your entire summer with massive plumes of smoke. So it really is a question of what are the relative costs and what are the relative benefits. And I think it's
Daniel. Sorry, I was able to unmute myself, and I just want to expand on that. First of all, I'm a big fan of yours. I follow you a lot on Twitter and so forth. I work in San Mateo County, and I was actually on a call about CEQA for prescribed burns, and that's where the question came from. And I was astounded that the number of public people that were opposed to a prescribed burn. There was one person that was supporting it, and 5 or 6 were opposed to it. And it didn't make any sense to me, particularly after the summer we had last year. And then on top of that, you got to get through the Air Quality Board and all these other folks. I mean, I work with these fire people, and they know what they're doing. So how do we get the public to buy into this? That's really the high end part of it.
I think public buy-in is actually, aside from the lack of funding, so even if there were public buy-in, we wouldn't have the money to do it. I think that the public buy-in is the biggest problem, and perhaps that's part of the reason why the money isn't there. But it's, that is going to be a big challenge, and I don't have any good answer other than, I think that it's important to be able to demonstrate that we can do it safely. So we need to continue to escalate, where we're doing it now. Mostly these burns are done in areas that are pretty far away from where people live. So highlighting the successes, and there have been many. I mean, some of the fires last year that didn't become catastrophes because there'd been a prior prescribed burn treatment nearby. So as bad as last year was, it actually could have been significantly worse had there been no prescribed burning over the past decade. So I think it's a hard sell from an air quality perspective too, because no one likes smoke. But I think it's partly a public education. I mean, I think that eventually, I think it's possible to win over the air quality control boards. It's possible to, I mean, I think CAL FIRE already wants to do more, but they feel beholden to, things that have nothing to do with fire safety, So it is largely an image problem. So I'm hopeful that we can work on that a lot in the next few years.
Thanks for the question, Michael. Rex Sanders, you had a question. You want to unmute yourself and ask your question? You're still muted. Can you unmute there? There. Oop. It's when it reverted back. You go. There you go.
Okay. So for a series of articles I wrote last fall on wildfires in the West, I was astounded when I dug into some Forest Service statistics, and it showed that in the first roughly 20 years of the 20th century, the average acreage or square miles of wildfires in the West was roughly 5 times what we've seen over the last 20 years. So that really put things in perspective for me. I kind of wonder, I mean, you carefully compared our current flood regime to an event from the 1800s, but it seems like we've lost the context of massive wildfires historically. And even a local historian here in Santa Cruz County used to talk about wildfires running from one end of the county to the other in the late 1800s. So what's your perspective on this historical version of wildfires in California?
So I guess I'd have 2 main points. The first of which is that it's very clear that, as I mentioned, that there was a lot more fire prior to our 20th century or early to mid 20th century period of total fire suppression in the American West. So obviously the amount of fire in the landscape decreased a lot over that period, which is part of the underlying problem. But the difference between the fires that occurred, 100, 150 years ago and the ones today is those were vastly different fires in terms of the character and the intensity of those fires. So they may have been very large fires, but they're a much lesser intensity, vastly less. And they were, in a lot of cases, mosaic burn patterns. So the Forest Service themselves actually say that those numbers from the early 20th century are probably significant overestimates because we didn't have anything like satellite fire mapping or aerial fire mapping back at that point. So we don't really know how much of these perimeters actually burn. So it's sort of an upper bound. But their broader point stands that there was a lot more fire on the landscape 150 years ago than there is now, which really just speaks, but the key difference is that intensity. So those were pretty low intensity fires, the ones that were burning sort of unmitigated across the landscape. And a lot of the acreage that was burning in those fires was grassland. So 150 years ago, a pretty significant portion of California kind of looked like the Great Plains in the Central Valley, ringing the foothills. So it's very easy to get a 1 million acre grass fire. Sometimes that even happens today on the Great Plains, even in our era of modern fire management. But a 1 million acre forest fire is pretty different from a 1 million acre grass fire. So, and the intensity that we're seeing today is having really transformational effects on ecosystems. And also, there's a lot more people living on that landscape than there were at that point. And there's not necessarily a value judgment passing on that, but that's just the reality, is that there are lots of towns and cities that weren't there before. And there's more at risk when these huge fires do occur. So the historical context is interesting, but I think it's important to keep in mind that, as I was really trying to emphasize, it's not the scales and spatial sense of the fires so much that's the problem. It's the intensity.
Thanks for the question. Someone has asked about hardening homes to prevent more damage to those homes, and mentioned something like ember excluders. Is that an option to reducing the destructiveness of these fires?
It certainly can be. I insisted that my parents put spark arresting vents on their home just this last year. So there are actually some pretty simple interventions that can be done for structures that are already there. There's also, more sophisticated interventions, when new buildings are being constructed or when places are being remodeled or something. There's a whole lot that can be done. I mean, in Australia, there's a lot of regions now where all new homes are designed to be, fireproof is a strong word, but they're a lot more fire resilient than the typical home in California. And, it partly has to do with the building materials themselves, and what you put around the home in terms of the vegetation that grows right up near the home. So there actually is quite a lot that individual homeowners can do that actually makes a surprisingly big difference. It doesn't always prevent a bad outcome, but it prevents a lot of bad outcomes. When you have a giant ember storm and 60-mile-an-hour winds, you do your best, it might not work. But in most other cases, I mean, most fires aren't occurring under those conditions. And on those slightly lesser conditions, these interventions make a huge difference.
Thanks. Madeline Nash, you had a question. You raised your hand.
I'm unmuted. How are you? Nice to see you. I wanted to ask and switch back to away from fire for an instant. We can go back to it, but I wanted to ask about the change in seasonality between the rainy and dry seasons. What aspect of climate change would be driving that, first of all, and also, is it something that's going to continue? Are we going to continue shrinking the rainy season, or other things? I mean, or maybe we're gonna get rain in June or something. I don't know.
Yeah, we really expect. I would say that unfortunately that sharpening seasonality is likely to persist and amplify further. So we'll probably see even a greater delay in the autumn rainy season and maybe an earlier termination in the spring. So that's something that I would expect to continue. If you recall the very beginning of the talk, I was talking about how we sort of lie on this boundary, this climatological boundary between the subtropics and the mid-latitudes. What's essentially happening in a warming climate is the subtropics are expanding. And that's why I mentioned that most of the other Mediterranean regions on Earth, which also lie sort of in these subtropical boundary regions, are becoming drier on average. Now, what's interesting is California is not getting drier on average, as I mentioned, unlike all these other Mediterranean regions. And the singular reason why is the winter response is different than all these other Mediterranean regions. So the rest of the calendar year, what's happening in California is very similar to what's happening in Spain or central Chile or South Africa, in the sense that it's getting drier, we're getting more subtropical. But in the winter, we're not. And what that means is that we still get that winter precipitation. We might even get a little bit more winter precipitation, but the rest of the year, we're essentially increasingly under that subtropical influence. And so what we'll essentially see is an expansion of summer by a month or two in either direction. We'll still have winter, or a brief period in the middle there for a few months each year. But it's essentially we're going to lose spring and fall, at least as we traditionally define them. So that's sort of what we expect the future to look like in a somewhat extreme simplification. We go from having 4 seasons to kind of having 2 seasons, winter and summer. I know some folks say that's what California is already like, but it'll be even more like that. Is sort of what we foresee.
And what's the future? What's the future of the RRR?
Well, it's back this year, and really, whenever we have a dry winter, that's kind of the mechanism. So, we say that we're going to have more dry winters as well as more wet winters. Those increasing number of dry winters will be associated with patterns like that, with the some sort of resilient high pressure system.
And that pattern is coming from the expansion of the subtropics?
It can be. It's a little bit different in winter, though, because we're not necessarily seeing that expansion in winter. So it kind of helps us explain what's going on in autumn and in spring and maybe in some, but less so in the winter. So the winter is a slightly different thing. And we're still trying to figure out exactly why we get more of the ridges in addition to more of the troughs, since it really does look like we get more of both. And that's a sort of an interesting, quite open question.
Maybe you could explain a little more what you were talking about. Madeline mentioned RRR, which I guess is a ridiculously resilient ridge, a name that you perhaps gave it. What is that, and how does that relate to the weather around here?
Yeah, the ridiculously resilient ridge was just a sort of a tongue-in-cheek term that I coined on the Weather West blog back in, I think it was 2013, so a while back, at the very beginning of California's last big drought, to describe this really persistent region of atmospheric high pressure that was recurring and really just stagnating over the North Pacific. So really what it does is it physically blocks the storm track. Think like a boulder in a stream, kind of literally, because it is a mass of air, extra air mass, literally, which is what high pressure is, deflecting the fluid flow of the atmosphere. In this case, the jet stream, that river of high velocity air in the upper atmosphere, away from California during the wet season. So the analogy is actually pretty literal, more so than most in the science communication world. But it's really just this feature, and it's not there all the time. It doesn't mean that there's high pressure that sits there and then doesn't disappear at all for even a day. You know, it comes and goes during the winter, but really what it's meant to connote is this feature that is there more often than not when it shouldn't be. And so this past winter is a good example of that. There were a couple of decent storms, but for the most part, we were under the influence of this high pressure system for the vast majority of the winter. So that's sort of what I'm talking about there.
Kenneth had an interesting question about Arctic changes and how that might affect California weather.
It's really, yeah, there's been a lot of really good questions that actually get at some of the research topics that are pretty active still. So you might ask some people and they'd say probably nothing direct. I would actually give you a slightly different answer. I think there might be something there. And it's actually a pretty contentious topic in atmospheric science. There are, unlike most physical science research in the climate world, there are actually two camps right now of scientists, almost evenly split on whether or the degree to which the fact that the Arctic is warming much faster than the rest of the world is affecting essentially weather patterns in the mid-latitudes. It's clearly affecting weather patterns in the Arctic and subarctic. There's no question about that. But the question is it having a direct influence on weather at our latitude, you know, in the mid-latitudes or even the subtropics? And the answer is maybe, but not necessarily in the way that you think. And what's so fascinating is that some of the research on how it might affect the North Pacific and California have come to almost diametrically opposed conclusions. There's been at least one recent paper that suggests that amplified Arctic warming could enhance things like the ridiculously resilient ridge and make persistent high pressure and drought more common in California. There is another paper that suggests precisely the opposite, that this loss of sea ice could actually lead to much wetter winters and could actually be a mechanism explaining why climate models suggest that we actually might get a little bit wetter in winter as opposed to drier like the other Mediterranean regions. And then there's other work suggesting that it actually may vary season to season. It could be part of the reason why the autumn is getting so much drier and warmer in California. It may favor a big ridge in autumn that unfortunately would have big implications for our fire season, but could have the opposite effect just a few months later in winter. So I think the jury's still out on that one. We really just don't know. There really could be something there, but it's awfully hard to discern right now. So that's going to be an ongoing topic of research for quite a while, I think.
And another person has a question about future cyclones, tropical cyclones coming up into California. Is that a danger that we have to worry about?
Yeah, it's another good one. I actually thought about asking that one as part of my PhD thesis and then ended up not asking it because as I'm going to answer, the data is really sparse. But speculating, I would say yes, not by a lot, but by at least by a modest amount. If you look far enough back in recorded history, there actually has been a hurricane landfall in California, in San Diego. I think it was the Great San Diego Hurricane of 1858. That was a pretty interesting decade in California weather, I guess. But there have also been a couple of tropical storms that made landfall in Long Beach and south of Santa Barbara. So there is some precedent, at least in Southern California. It's a lot harder in Northern California because the water is dramatically colder. And these are storms that occur, just for everyone's reference, in the warm season. So these are not winter storms. Hurricanes and tropical cyclones are fundamentally different meteorological phenomena from winter storms, and they require very warm oceans. We do not have a very warm ocean off the coast of California, but we are relatively close to a very warm ocean off the coast of Baja California. So if a large or strong hurricane does develop west of Baja California and manages somehow to get on a northward trajectory at a high rate of speed, it doesn't have time to weaken before it gets here. That's essentially what happened in the 1858 hurricane, the 1939 tropical storm. That would be the same mechanism as what would happen if this were to happen in the future. And because climate change is increasing ocean temperatures, you might have a slightly increased likelihood that you'd get a strong enough hurricane moving quickly enough to have that effect. So yes, but I don't think it's ever going to be a significant common problem in California.
Good. Is there any good news for the future?
Well, I think the good news is that, you know, I often get, well, and honestly, I've gotten a lot of very, you could even call them panicked emails, especially from young people even younger than myself. It's really interesting. These come a lot from high school students and college students in the past few years, who are genuinely concerned that the world is effectively ending as a result of climate change in a very literal sense. This notion that there is like a geophysical cliff. And it turns out that what happened was some messaging from the IPCC and from the Paris Accord and from certain environmental activist groups has gotten really mangled. And there's this notion that the reason why we're trying to avoid 1.5 degrees of mean warming globally, or 2 degrees of mean warming globally, and the reason why we've set these target dates like 2030 or whatever year, is because at that specific point, all hell breaks loose, everything falls apart, the climate system goes suddenly haywire, and the warming becomes self-sustaining and uncontrollable. The good news is that's not our understanding of how the climate system works at all. And the good news is that, you know, I think it's extremely unlikely that we hold warming to 1.5 degrees globally. That just seems exceedingly unlikely given practical realities. 2 degrees is possible, maybe if we're really lucky, but still seems unlikely. But the point, what I really want to make is, you know, 2 degrees is definitely worse than 1.5 degrees, but it's not the difference between the end of the world or not. And so, you know, 2.1 degrees versus 1.9 degrees, they're actually similar outcomes. I think objectively, you know, from a societal standpoint, it's better that we end up lower than higher, but every increment of warming that's avoided will avert a lot of societal and environmental harm. And so it's not like you lose all hope beyond some specific threshold. It's not like if you were not successful at 2 degrees and then we ultimately keep it to 2.2 degrees that, you know, we failed. That will still be a huge success relative to the trajectory that we're currently on. And so it will never be too late to make progress on this. So I think that's one of the optimistic views. And the other is that even in the meantime, given that we know we're going to have at least some amount of additional warming, probably a significant amount of additional warming, and some additional increment of increase in these extremes, which are harmful objectively, there's a lot we can do to mitigate those outcomes, even knowing that they're going to happen. So even given some additional increment of warming and increase in extreme events, those don't necessarily have to lead to increase in harm. You know, we can decouple wildfire from catastrophe. We can decouple flood from catastrophe to a large extent if we do the right things. Arguably, we're still not doing those things either, in addition to not doing enough to bring net carbon emissions to zero. But those are both things that could be done. And the good news about the latter one, some of these adaptations, is they will have effects, tangible effects immediately. It's going to take a fairly long time to turn the ship global climate wise, but a lot of these regional and local interventions bear fruit almost immediately once they're implemented. So I think that's my optimistic take on things, I'd say.
Well, thanks for ending on an optimistic note. I think we all want to thank you for a really stimulating talk, and I hope I caught everyone's questions. And if not, you can always email Daniel, I suppose, and ask him those further questions. So again, thank you very much. And thanks to the audience. We had a huge turnout. The topic was obviously very interesting, and I hope you enjoyed the talk.
Well, thank you all for joining me. And it was a great audience. Those are some really good questions. I often get research ideas from having these sorts of conversations. So we'll see what comes of it.
Too many research ideas to actually deal
Oh,
with.
far too many, but I can give them to other people, so it works out.
Great. Thank you, everybody, and thank you, Daniel.